The next chapter is on normal subgroups. Chapter 9. Okay. Normal subgroups and factor groups. Okay, now definition. Let G be a group and H a subgroup of G. Then H is normal in G if AH is HA for all A in G. Okay, we denote this by H. The sharp one is the subgroup, because if you, there's a subgroup, right? And this means it's normal. Okay. There is another one with a dot inside. That's not in this class. You can find out what that is. Okay, so that's another. This is normal in G. Okay, now how do you check a subgroup is normal or not? This is the left coset. This is the right coset. Okay, if G is abelian, then these are equal. We have seen this when we do coset last class, right? A plus H is H plus A because it's abelian. Okay. But you see, if you have done for S3, last time I mentioned about S3, you multiply on the right and on the left is different. Okay. So for non-abelian group, some of them they are true, some are not. But in general, if it's non-abelian, you have to check. Okay. Not necessarily normal. Then all subgroups thus of an abelian group is normal, are normal. In the group. Okay. So we don't normally check for abelian group. We check for the non-abelian group. Okay. Now normal subgroup test. Okay. If you don't have this normal subgroup test, you imagine you have to list all left cosets and all right cosets. There might be many. But to show that a subgroup is normal, you can also use using this subgroup, normal subgroup test. Okay, again, let G be a group and H subgroup of G, then H is normal in G if and only if X inverse HX is a subgroup of G. Okay, remember just now, this is the definition of a normal subgroup. Okay, XH is HX. Now you bring X to the other side, or bring this X to this side. Okay. And instead of getting this, since this is always a subset of this, okay, this is always a subset of this, we just show it one way. Okay, this is always true. Why this is always true? If you take one element H and X is in G, you multiply this is close, right? So you can show it clearly, but you can just show this way. Okay, or you can show H is in H, X inverse HX is element of H. Because this means this is what it means by subset, right? A subgroup. If you take one element in here, then it has to be in here. Okay, so you take element in here, it has to be in, multiply in. So X inverse HX. So this actually is the easiest way to show that it's normal or not normal, right? Not normal is easy. Just find one X, take the inverse, multiplied by element of H, multiplied by X again, see if it is in H or not. If it is not in H, it's not normal. To show it is normal, you have to try all. You have to try all and show all. Okay. I mentioned earlier, okay, this is one mistake. This does not mean this. This does not mean this. This is just abelian, so that's why if it's abelian, then it's okay. It's actually means this. X times one element of H is another element in H times X, H prime. Okay, that is another element. So it doesn't have to be the same H, right? Because this is the subset or subgroup, not just one element. Not necessarily the same H, as long as there is another one. Okay. That's theorem. Every subgroup of an abelian group is normal. Okay, you can go through the proof. It's very straightforward because it's normal. You can just multiply, right? This one is even equal, right? The H. The center is always normal. Okay, so the center is always normal. How do you prove this? You take one element in the center, right? And element in the center always commute with all elements. So that's why you have element in the center, G in G. This is always true. So it goes back to the definition of the normal subgroup. Okay. Another one is The first one is, if it's abelian, then all subgroups are normal. Okay. The second one is the center is normal. The third one is, what's the third one just now? Oh, AN is always normal in SN. Okay. Even permutation is always normal. If H1, H2 is normal in G, then the intersection is always also normal. I am not going to give the whole proof, but you need to go through in the proof. Okay, it's quite easy. Assume this is normal in G, so you will have G inverse Hg is element of H. This is also normal. Then you have to show the intersection is also normal. So take one intersection in here and G inverse multiplied by something in the intersection, show that it is also in the intersection. Okay, so you follow through the proof is straightforward. Okay, this is very important. If the index of H in G is 2, then H is normal. This is one reason why this is normal, because the order of because the index of Sn in An is the order of Sn divide the order of An, and the order of Sn is n factorial. The order of An is n factorial over 2, so it's 2. So if the index is 2, then it's always normal. This is a very famous theorem, and it's quite easy to prove. Okay, because how it is easy to prove. Suppose G is a group and H is a subgroup of G. Let the index of H in G is 2. Then G has 2 left cosets, H and GH, where G is not in, right? Okay. G has also 2 right cosets, H and HG. Okay. So since G is not in H and there are only 2 cosets, HG has to be equal to GH, because there are only 2 cosets. H already equal, G is not in H, so HG is GH for all G. So H is normal, right? Okay, the others are quite straightforward. Okay, this is another interesting group came up from this chapter, a simple group. Okay, a simple group. A group G is simple if its only normal subgroup are the identity and the group itself. Identity subgroup or the trivial subgroup. A group G is simple if its normal subgroups are the identity subgroup, which is the trivial subgroup, or the group itself. Okay, meaning G has no proper non-trivial normal subgroup. Okay, so if you have this E, this H, this G, G is simple if you don't have this H normal. Okay, G is simple if it has no proper non-trivial normal. So this cannot be normal. Okay, and the only normal will be this and this. Otherwise, we will say G is not simple. Okay, for example, just now we have seen N is a normal subgroup of Sn, right? So we say Sn is not simple. But this is for just certain N. If you look at the I think it's for all. Probably it's true for all. So Sn is not simple. There is a normal subgroup inside, so Sn is not simple. What about Dn? Dn is also not simple. Because in the dihedral group, half of it is rotation, right? Half of the Dn is rotation, including the identity R0. So the rotation, half of this actually, and it is normal because its index is 2. The index is 2. That is a joke actually. I remember my professor gave me this joke that he said only the pure mathematician or those taking group theory that knows this joke. Okay, it says there is this group of students walking around, and the professor saw this group of students, and the professor said, "Wow, this is a simple group." Okay, so if you don't take this, you don't understand what is a simple group. You will say, "Thank you, professor," right? But the truth is, the professor is saying, none of this student is normal. That is what it means by a simple group. So a joke that not many people will understand even. What are you talking about? So if people say you are simple, you said, do you mean it as a simple group or do you mean it as simple English? So simple means none of it is normal, none of the subgroup. Okay. All right, so then we come to the factor group. We need to have a normal subgroup before we can go to factor group. Okay, so if you don't have a normal subgroup, you won't talk about the factor group. When you do rings later, this is what you call the, what is the I in the ring? Ideal. Okay, it's like you handling ideal in ring later. So question will be, given a subgroup H of G, show that H is normal or decide whether H is normal or not. Okay. When the case it is normal, then we call and define a factor groups. Okay, we have a definition there. Okay, let G be a group and H is normal in G. Okay. Then the set of left or right cosets of H in G forms a factor group of H in G. So we call it this. Sometimes people call it factor group. Sometimes people call it quotient. Okay. And G mod H. This is what you say. G mod. So this is A or G, GH, G in the set of all left or right cosets. Okay. Let's look at an example. Okay. The simplest example would be Abelian group. Okay. And H generated by 6 of order 3. 18 divided by 6 is 3. Or you can do 0, 6, 12, and then 18, right? Which is 0. Z18 is abelian. So any of the subgroup would be normal. Okay, you know 18 is 2 times 3 squared. So if you need to find all subgroups, okay, if you need to find all subgroups or any p times q squared, if you list the lattice subgroup, the lattice diagram is generated by 2 and generated by 3 because it divides 18, right? So 18 2, 3, 6,
9.
9, 18. 1, right? That's it. Okay, so there's a t squared. So underneath there's a 9. Okay, and 2 and 3, there's a 6. So you have 1, 2, 3, 6, 9, and then this is the, okay. If there is a 3 cube, then there will be 3 squared, 3 cube. And then multiply by the 2, that's another one. So let's just subgroup like this. So these are the list of all subgroups, which is cyclic, which is normal, they're all abelian for Z18. Subgroups of cyclic group is cyclic. So I just take one. I just take this one. You can try this example with 1, 2, 3 other proper subgroup. Okay, it's a good exercise. I will just do with one. All right, so you can try with 2 or 3 or 9. Okay, so this is the coset. You remember to list all coset? One time I just write it out, next time I don't write it out. This is to show from yesterday, right? You don't have to do this. Don't do this in like listing all the elements. I'm just showing you. So H is, this is 0, 6, 12, right? And that's what we do. The index of Z18 in H is 18 over 3, which is 6. So you will be expecting 6 coset. Okay. Then you cancel 0, 6, 12. Okay. The next one would be 1 plus H. So you get 1, 7, 13. Because we're just adding 1. And you do 1, 7, 13. You can see the pattern already, right? So you will go 2 plus H, 2, 8, 14. 3 plus H, 3, 9, 15. 4 plus H, 4, 10, 16. 5 plus H, 5, 11, 17. I think we are covered all, right? Okay, this cover all. If you cancel, they're all inside already. And this, even if you want to go the next one, 6 plus H is again this, right? This is 6 plus H. So 0 plus H is equal to 6 plus H is equal to 12 plus H. So your coset becomes the element of the factor group. So this becomes H, 1 plus H, 2 plus H, 3 plus H, 4 plus H, 5 plus H. Okay, now this is a set, right? This is a set of order 3. Okay, this is a set in a set. They are all a set of order 3. I don't put them as sets, but we say the order of this is 6. 1, 2, 3, 4, 5, 6. We don't say the order of here is 3 anymore, because this is a group of order 6 with the 6 elements, and this is actually the identity. This is the identity of this group. Now this has order 1 as one element in the factor group. Okay, So how do we multiply? Then we can do Kelly table. But for this one, this is also equal to H plus 1. Because abelian, right? So left and right, they're all the same. Okay, let me write out the Kelly table. Actually, I don't want to do it, but okay. The Kelly table will be H1 plus H, 2 plus H, 3 plus H, 4 plus H, 5 plus H. And this is a plus, right? H1 plus H, plus H. Dot, dot, dot. Not enough space. 3, 4, 5. Okay, so 6, 6. Now, you have to think of H as 1, although it has 3 elements. Okay, it is the identity. How do we add last time? This is what we defined before, right? This is how you add coset. Oh, I haven't defined. Or this is how you multiply coset or operation of coset. So how do you add? What is H plus H? There is a 0, right? 0 plus H plus 0 plus H is 0 plus H. So 1, 2, 3, 4, 5. And that is why I said that this is the identity, because this is same. And this, when you add the representative. Okay, what is 5 plus 1 plus H? 6 plus H. What is 6 plus H? H, right? And so on. And you can show that this is isomorphic to Z. You can map this to 0, this to 1, this to 2, to 3, and so on. So this is actually isomorphic to Z6. It's cyclic of order 6. And if I ask you now, what is the order of each element? This has order 1, this has order 6, this has order 3, this has order 2, this has order 3, this has order 6. So they are don't get confused with the element as a set of certain order. Okay, it is an element, although it's a set, it's one element, and the order depends on how many you add to get the identity, which is H. Okay, this is quite straightforward because this is abelian. Then, as before, if you choose the subgroup of order 2, then there will be factor group of order 9. Okay, if you choose a subgroup of order 9, then you just have a factor group of order 2. Okay, so for this. Okay, next is S3. You have learned of this, right, for modern algebra? No? You remember not? Like G is S3. Now, you need to check, you remember all different subgroups of S3? S3 has order 6. It has 1, right? Cyclic subgroup of order 3. And it has 3, right? Cyclic subgroup. 1, 2, 1, 2. These are all the subgroups of S3. Okay? One subgroup of S3 of order 3, 1, 1, 2, 3, 1, 3, 2. 3 subgroups of order 2 and the trivial subgroup. Now, if you check, none of this is normal. These are all not normal. And you can check if G is in S3, say H is generated by 1, 2, you take maybe something in G inverse, HG, then you can easily show it's not in H. Probably take something like 1, 2, 3. Okay? 1, 2, 3 times 1, 2 times the inverse, right? 3 to 1. So 1, 1 to 3, 3 to 1, 2, 2 to 1, 1 to 2, 2 to 3, 3 to 2, 2 to 1, 1 to 2. Okay, this is an example. How do you show that this is not normal in S3? For example, take one element in G, G inverse H, G. If G is 1 to 3, multiply, is not in H. Okay? So you don't have to list all left coset, all right coset. You just take one element, show. So actually, the only normal subgroup is this one. S3 has only one normal subgroup. And also the index is 2, right? 6 over 3. And this is also A3. Oh, so many reasons. And H is A3. Generated by 1, 2, 3. Now we have only 2 coset. Okay, so A3 is 1, 1, 2, 3, 1, 3. So, okay, so call this H, right? Then you get confused. Which is equal to 1, 2, 3 H, which is equal to 1, 3, 2 H. And the next one is 1, 2 H. Take one element S3, which is not in here. Okay, take one element in S3, which is not in H. So multiply. You get 1, 2. What is 1, 2, 3 1, times 1, 2? On the left, yeah? So 1, 1 goes to 2, 2 to 1, 2, 2 goes to 3, 3, 3 goes to 1, 1 to 2. So this is 2, 3. Another one is 1, 2 times 1, 3, 2. So 1, 1 to 3, 2 to 2, 2 to 1, 2 to 1 to 2. So this is 1, 3. Just enough, because we have now enough elements. Remember, coset is a partition, so you have partition into 2. So this is a subgroup, this is not. So this is the factor group. Call it H, right? And 1, 2, which is isomorphic to Z2, cyclic subgroup of order 2. Easy. The Kelly table is just 2 by 2. Okay, a Kelly table is in the notes. We can also have this third example of infinite numbers, infinite groups. Okay, for Z. So the third is, you can show Z and Z is isomorphic to Zn. Okay, if you have Z and 2Z, one even, So the coset will be 1 even, 1 odd numbers. So you have 2 cosets. Okay, isomorphic to Z2. Okay. The last part is on the internal direct product. I mentioned this when we do the chapter 6 direct product. That there is also an internal direct product. I will just mention it here. Okay. Okay, first we define what is HK. Just H times K, H in H, K is in. Sometimes when you multiply, it's not the whole G. But if G is a product of 2 subgroups, you multiply, you get the whole G. Okay? Now, what is the internal direct product of H and K? Okay? This is just the definition of the product. Okay? Let H and K be 2 normal, has to be normal subgroups of G. Then G is the internal direct product of H and K. Okay, if it satisfies 3 properties. G is a product of H and K. They commute. And they don't intersect. Okay. Okay. Now, last one. Hannah, you note in my, if it's not there. Do you see semi-direct product? It should be last part. Hmm? Okay, I will add. After this, just edit and add in the next place. Semi-direct product, eh? Okay. Let H and N be 2 subgroups of G. G is a group. Then G is a semi-direct product of H and N if wait, let me write G equal H and H. G is a product of 2. N is normal in G. Only one is normal. Just now both have to be normal. Only one is normal. The third one is the same. Example? Or the example of direct product is this. This is internal direct product. Okay, Z2 cross Z3. This is example is dihedral. Okay, dihedral. Later on, I will explain. This is the rotation. Okay, this is the rotation of order n. This has order 2n. This has order n. So the index is 2. So it's normal, right? So this is the normal one. This is the other one, the reflection one, okay, which is not normal. That's an example of a semi-direct product. Okay, I will stop here. Let me add another assignment which is due not next Wednesday, but the Wednesday after. Okay. Assignment number 4, right? Due on 16th of 12. Already end of the year. Okay. It's quite easy. 6, 14. I mentioned about this, but let me see if you can do this. 21. $42. 1, 2, 3, 4, 5. All right. So no class next week, but I share already seminar. Okay, seminar to get bonus point next week for 1 hour. Due on Wednesday next week, right? The assignment 3. Okay, and we will meet again on Monday after next week.